So maybe then you want to put it on a podium, or we can move pizza somewhere. Yes, there's one. Wait, okay, this is running.
In a Mac. You can use this table. You can use this table.
Yeah, let's.
Oh, that's.
Remove it to the. Yeah, we're doing after high quality. This is something that we like C++ and like so. We're talking about this. I don't know. What do we do? So maybe join. Oh, okay, I have to send you.
Oh, it makes it layer templated. And then you have to under the you need to pick which one. Oh no. Dude, don't it's beautiful. As much as I hate C++ templates can be fun.
So yeah, you're wrong, but I don't know why.
That's so funny.
They are not.
I think it's funny because you never benchmark if it's after right now.
Mirror extend display.
It's faster than before. You said before
screen.
with that.
Somewhere here should be mirror display.
I'm just gonna say it's
Probably this. Yeah. Screen mirroring. I don't know, click.
It's connected.
But why no, not there?
I'm gonna stop share yours and then
What do we do? I usually
there, then
stage mode or screen mirroring.
should be screen mirroring.
So this is something. I'm not an expert, honestly. So what do we
Maybe
do?
choose content here. Choose content. Choose content. Then entire screens.
Screen display. Or you
I
want?
think start entire screen. I think we just want to show.
Yeah, it's there.
I was thinking. I think the company
I don't want to enable your camera. So you can remember your.
Then
You guys just like to set up the context. Remember, I said that first of all, I don't understand this new EFDF scheduler, which is what earliest something deadline, virtual deadline first, which became de facto standard in Linux. And Yado went and kind of figured it out, and he will. And I said, okay, sure. Essentially, you read the source code, right? Because that was the best, most reliable source of explanation, plus some additional emails online, which explain why they moved from completely fair scheduler to this one. And honestly, I still don't know the reason, and we should discuss and figure it out today together. And I'm new to this, same as you, so we will have to make sure that we understand it. Maybe you want to plug it here. Oh, you don't have USB-C here. Wow, that's cool.
I think it should be okay.
I do actually have. Okay, so that's the prequel. But so yeah, sure. Go ahead.
I just want to preface by saying I didn't figure out EVDF completely, but I did go through the code and I have a good idea about it. So I think it'll be more of a discussion than a course on it, really. But what we'll go over is just exactly what we're trying to achieve with fairness in Linux. And then we'll look at what CFS does and how EEVDF kind of compares. So first we'll go through the slides. The first slide is going to be, I think I opened the wrong slide deck. Sorry about that. One. Okay. Yeah. So first we'll go over exactly what we're going to kind of cover today. We'll go over what exactly fairness means in Linux. It's really what we're looking at in terms of a trade-off between responsiveness as well as throughput, um, as well as predictability. What we want to do is basically make sure that low latency tasks do not suffer. They are pretty responsive. We want to make sure that CPU bound tasks get fair share of CPU as well. And we want to make sure all of this happens proportional to their priority. We don't want to forget that while we're going about the trade-offs here. And the big part here is the predictability, where we want similar tasks to get similar service regardless of when they wake up and any other kind of external factors. What CFS does is by tracking just V runtime. This is the entire logic of CFS here. And the real beauty of CFS is really that it takes all of this fairness logic and encodes it into one comparable metric. It's just V runtime and nothing else. And in doing that, I think they've kind of made it simple as well as opened themselves up to a lot of caveats, a lot of different scenarios that they had to kind of tune CVS for. And that's what you see in fair.c. So if you go through the source code, this is the source code for 6.5.13. Which is the last version that CFS was present in. And at this point, it was around 13,000 lines of code. But when it started off, it was just about 3,500 or so. So it's kind of increased over 17 years from 3,000 lines to 13,000 lines, which kind of shows that they really approached it with a very simple mindset. And they had to add a lot of code to kind of make up for those caveats that they kind of encountered. And what we're going to kind of discuss is exactly what the difference is between CFS and EVDF, how they go about trying to kind of implement this fairness in the scheduling process. We know that we've already discussed CFS a little bit, and what it does is track the smallest VRAN time. We'll go over the different data structures and different functions in CFS to really understand what it does, because it's really in comparing CFS and EEBDF that we really see the difference or advantages that EEBDF brings to the plate. So we'll start with CFS first. And what we're trying to do here is kind of simulate an ideal multitasking CPU. If you have n processes, the ideal multitasking CPU would run all of them at the same time, and they would all get the fair share of CPU time simultaneously. But we can't do that in the real world. It's discrete scheduling that we have to deal with. And because of that, we try to approximate it by just using virtual runtime. So this is both the beauty as well as the drawback of CFS that tries to encode all of this complex logic into just one metric. So it does that by using a red-black ordered tree, where the leftmost node has the least vRun time, and we always run the task with the smallest vRun time. So we'll kind of go into the execution flow of this in depth so that we understand how it works. Yeah.
Is V runtime the length of time it has already run?
Mhm.
Okay.
Yeah, but then it's kind of scaled by weight. So it's not the actual wall clock time, but it's the wall clock time, the CPU time that it's run, scaled by the weight of the process itself. So the VRun time grows slowly for highly prioritized tasks. So it stays on the left side of the RB tree for longer and is scheduled more frequently. So that's kind of how this kind of logic works. But when you go through the execution workflow, it'll kind of become a little more apparent about how this kind of encodes all of that logic. It is just one metric.
And the weight, is that a priority?
It is, yeah.
Okay.
So this is kind of where we'll start understanding exactly how vRun time goes about the fairness of it all. So vRun time is the real star here. We're looking at two structs. One is for the task itself that is going to be scheduled at every scheduling decision, and the RQ tree itself. So in the task, it has the vRun time, which is the main guy. Everybody else is kind of like a supporting actor. Exec start is the last time at which it started execution. This is important to kind of know the wall clock time for scheduling. And that is kind of adjusted to get the V runtime later on. The sum exec runtime is just for stats. It's the total accumulated runtime over its entire lifetime. You have the load, which is the actual wait. You have the run node, which is the node in the RQ tree when it's part of the run queue, and the run queue that it's a part of. Now, this is kind of important because how CFS works, or even EEVDF for that example, is that it's a nested run queue. So you have a run queue per CPU, and in that one node can be for a C group itself. And that C group is a run queue of its own with all of the tasks within the C group. And all of this logic that we'll talk about is kind of the same. Only thing is it might kind of walk in the hierarchy of the nested run queue itself. It will first happen in the lowest level, and then it'll kind of climb up based on whether it's part of the C group or not. So if it's not part of the C group, it's just one run queue. But if it is part of the C group, it'll be implemented in the C group run queue first, and then it'll walk up to the CPU run queue later on. But the logic remains the same.
Are these groups based off of child processes or some grouping like that?
Not really. Child processes we will come to when we talk about buddy hints. So like child processes are looked as buddies, where it's waker, wakey, or it's rapidly spawned tasks. But C groups we're talking about when it's sharing CPU resources as well as storage. We're talking about the Linux C groups there. It's not really child processor. Yeah. And then that's just the structures itself. It's important to know exactly what we're dealing with so that it's clear to us when you go to the code. In the run queue itself, you have the task timeline, which is the RB tree, the current node, that is the current task that is running, the min-v runtime, which is the minimum runtime of the leftmost node, basically, and then the number of running processes. So now we'll go through a bunch of functions that are central to the execution logic of CFS itself. And we're only doing this to really understand exactly how all of that logic is encoded into one metric, as well as how EEVDF later improves on this logic. So what we're looking at first is the scaling function. So I told you that a task gets CPU time that is later scaled by its weight or priority. So this is the scaling function that does that. What it does is take the delta or the wall clock CPU time and then multiply that into the base weight divided by the weight of the process itself. So if you have a larger weight, it's scaled to a smaller value. If you have a lesser weight, it's scaled to a bigger value. So the V runtime grows slower for a larger priority process and grows faster for a lower priority process. Is that kind of clear?
So I think if I understand correctly, and maybe I'm wrong, so load is the number of processes running in the system?
No, load is the priority or the weight of the process itself. Yeah. Yeah. So basically, when we're talking about weights, it's from something called a nice value. And you have 0, which is the base nice value, which is 1024. So the nice value maps to the weight. And the highest priority that you can give it is +20, which is significantly higher. And the lowest one that you can give it is -19, which is the nice value itself, which maps to a weight that is significantly smaller. I think something like 10 or 30 or something, if I'm not wrong. But all of this is in powers of 2. That's to kind of optimize the update curve function that we look at next, because you want bitwise operations for something that's called this frequently and not division. But this is what the scaling function does. Is that kind of clear about how V runtime grows?
No.
Depending on the load?
Sorry.
Yeah.
How would you assign initial nice values?
So these nice values are initially assigned based on the kind of task itself. It's not really dictated by the task. I'm not really sure exactly how it's initially assigned, but each task has a nice value that the scheduler knows about. It's not assigned by the process itself. It is judged by the scheduler itself. It's judged by the kernel, if I'm not wrong. How is the nice value initially assigned, Professor?
No, I think it's just the policy that you can control from the operating system. When you give each process, I think default nice, and then you
Can
can
you increase it or decrease?
not really, you need pseudo rights or this nice capability to make it more higher priority, and then you can always drop nice. But I don't think it's done a lot, honestly, because
Is it set by the process itself? That's one thing. Yeah.
I think no, I don't know the answer, but I think it's when the process is created, you will get like the default nice.
Okay. Because in
And then
EVDF,
there is a nice tool which you can involve in cell.
okay.
You want to make something. I mean, we do it when we experiment with things and we say we want our stuff to run with the highest possible priority. Nothing else is running, but it doesn't really help that much. But
Okay. Because that kind of makes sense, because for EVDF, we have extra parameters that are kind of like, settable, it's configurable. I think nice as well is configurable, then in that case, that would make the most sense. But when there are tasks that are being scheduled, the scheduler is aware of the nice value, and the nice value goes into the logic of exactly how V runtime grows. And that is the core logic of CFS. It grows slower for high priority tasks.
So all processes will start on the left side of the tree,
Mhm.
but processes with a higher priority will just move slower.
Slower,
to
yeah.
Like towards. the
Which
right.
means that they are scheduled more frequently.
Yeah,
Which side is scheduled more frequently?
Left side.
Okay.
Because the leftmost node is what has the minimum V runtime and the RB tree at any point of time. So what we're looking at next is update curve, and this is the function that updates V runtime and kind of make sure that the RB tree is maintained as you go along.
I thought the CFS has this idea that you divide execution time fairly between the number of processes, right? So each gets a fair fraction.
Yeah.
Let's say you have 10, you get 1/10 of the CPU.
Mhm.
So is that the load or is it something else?
No, so basically we're talking about slices. So we'll come to that in a bit. But what we need to understand when we start talking about CFS is that V runtime is the start, and that V runtime grows quicker for higher priority tasks. That's just what I kind of wanted to communicate with the scaling function there. If we understand that, we'll come to a few more nitty-gritties and details about exactly how that is implemented and exactly how the execution flow works. So we'll come to the slices part next. But first thing that we need to understand is that the V runtime grows slower for higher priority tasks. And then we're looking at update curve, which is in charge of updating V runtime as we go on. So what we're doing here is we're determining the current runtime of the CPU, not the runtime, current time of the CPU. And then delta exec is the current time minus the last time that the task was started. So that gives us how long it is currently run for. And then we reset exec start so that the next time update curve is called, it's still accurate. And then we check. No, this is just to add the total runtime. This is just for stats. It's not a scheduling decision at all. But these three are the main lines here. So the V runtime is calculated by using the scaling function. It grows slower for higher priority tasks. After that, we add that to the current V runtime or execution time of the task itself. So it grows slower for high priority tasks. And this is important as well because it makes sure that the V runtime never decreases. It's monotonically increasing at all times. So it never decreases because it compares the min V runtime and the current V runtime of the current task. So what I mean by that is you have an RV tree, and for simplicity, we'll just forget about the middle part of the tree. We're just looking at the leftmost part. And this is the V runtime, min V runtime of the RV tree itself. Now we're checking the V runtime of the current task, and the current task is not part of the RV tree. It's dequeued when it's picked. And when we calculate the V runtime of this guy, we update the min V runtime based on whether it's lesser or not. But it never decreases. The min V runtime has to constantly increase so that the fairness is kind of executed and maintained over time. So we'll come to the execution flow later. But what we need to know here is that when update curve is called, min V runtime does not decrease. It's always increasing.
Sweet.
Yeah.
How is it even possible?
Yeah.
How is it even possible that it can increase? Because it seems that you're always adding to value and supposedly you pick the task with the.
Right. For a particular task, you're always increasing runtime here itself. But then that's where we're coming to the beauty as well as the drawbacks of CFS, because they're trying to encode all of that fairness logic into one metric. So when we're talking about waking up tasks, it's given a credit. So that credit kind of decreases the V runtime. And that is what we're kind of making sure doesn't decrease the V runtime here. But we'll come to that a little
Meaning
later.
that the
Yeah.
task would potentially start with the runtime, V runtime, which is
Lesser than min V runtime. Yeah.
and we let it run for a little bit, but then we still put it in the tree. Like the scenario which I'm concerned with
Mhm.
is that the task was sitting on a wait queue for a very long time.
Yep.
Everyone else progressed, everyone else's V runtime moved forward,
Yep.
right? That this task.
So we
gets
have a
scheduled for a
sleeping
little-
task which has a runtime of, let's say, 5 ms.
Mhm.
And then the min V runtime here goes to like 10 ms.
Yeah.
So this wakes up what happens then, right? That's what we're talking about.
Yeah, and the question, like, this is to prevent this task from monopolizing the CPU for a lot of time. Although
Yeah.
in some way it's fair because the task was waiting for that all this time, didn't get a chance to run.
So the way I've kind of made these slides is kind of like, growing into the logic itself. So you won't be clear about the logic from the start off. What we first saw is just the data structure itself of the task and the run queue. So what we understood here is what is the task, what is the kind of metrics we maintain per task and per run queue. And then we started looking at, okay, fine. If you go back to this slide here, we have the weights of each task, and how CFS tracks or progresses task is by looking at the virtual runtime. So that is done through the update cur function that we are looking at just now. So once we understand both of these, what we just know is that V runtime grows slower for higher priority tasks and V runtime never decreases. It's monotonically increasing. But all of these questions will come to later when we talk about the execution flow itself. So we're going over the NQ task, workflow here, which basically means that when you're adding a task to the RB tree, what we're really looking at. So this part is just to kind of show you exactly what happens when you're going over the hierarchy of CFS run queues. Like I mentioned, you have C groups. So if you have C groups, you kind of do that for each CFS run queue hierarchy. But this is to make sure that the logic, underlying logic is the same. It's just done at every level of that hierarchy. That's about it. Now, after that, you just update the current task and you place entity. This is really where we're looking at the wake up heuristics of CFS. And then we come to NQ entity where it's just placed in the queue itself. I think it'll be better now that I think about it if I go over the execution run flow first, and then I come into the nitty-gritties. So then let's go into the timer tick. Yeah.
Is the V runtime propagated when a process creates a child process? Does it get the same V runtime that has been updated, or it starts?
No, it's not related to the parent, but it is adjusted based on the RB tree. So I think coming to the execution flow will probably make things clear, and then we'll go into the details of it. So what we're looking at here is exactly how CFS goes about scheduling. Now, until this point, I think we've understood that V runtime grows slower for higher priority tasks and it never decreases. That's about it. So when we're talking about the execution flow, we're talking about exactly when the scheduling decisions are made and how they are reasoned about. Where's the duster?
You said V runtime never decreases. Are you talking about the min V runtime of the tree or each process's V runtime? Oh.
Yeah.
Okay.
So when we're talking about the scheduling execution flow of CFS itself, we're talking about the ticker and we're talking about wake up tasks. This is exactly when scheduling decisions are even made. So the ticker happens every 1 ms. And what exactly happens there is that every tick, you update the current task, you give it its fair share of runtime that is accumulated. And after that, you check if it needs to be preempted or not. And that is basically checking if it has run its fair share of compute that task deserves based on its priority. And if yes, it is preempted. If not, it is not. And then you are basically calling reschedule. If you decide that it should be preempted, and if it's not preempted, then you just go on kind of increasing its V runtime. The second is the wake up execution flow. So when a task wakes up, you activate the task, you enqueue the task, you give it its appropriate V runtime, which is done here in PSID. And after that, you check if it preempts the current task. So the rescheduling decisions are made one, every ticker, or two, when a task wakes up. And after that, we're looking at the context switch itself. So once you decide that, okay, fine, I need to reschedule, you pick the next entity, which is just the leftmost node in the tree. And after that, you update the current statistics, you enqueue the previous task, and you just remove the current task. So that's exactly what happens. It gives you a big picture of exactly when rescheduling decisions are made. But now we'll go into the main nitty-gritties about exactly where the complications come in. Yeah.
Can you just show the wake up small again?
Yeah.
Oh,
Okay.
all right.
Yeah, maybe can you go one more, but one more. So So what happens here, so
Yeah.
you have a timer every 1 millisecond.
Mhm.
And then what you update current with the current whatever,
Mhm.
be on time, we just looked at it, like minimum whatever.
Yeah, so this is just for the current task that we have, so it's better if we kind of visualize it as one RB3, which is all of our tasks that we have to kind of schedule between, and the current task, which is not part of the RB3 when it's baked. So every timer you kind of update current, you check if it needs to be preempted. That's all you're doing. And the preempt itself is gonna just check if current has run more than its fair share of CPU. And that fair share of CPU is determined by slice. So this is kind of where I think I'll come to the point that you made initially about what is slice, how is preempt tick really working. So if you have no IO bound tasks, just CPU bound tasks, exactly when is that CPU bound task preempted, and how is the CPU kind of reasoning between has it run its fair share of CPU or not? That I think it's best if we look at the code. Yeah.
We can come back, maybe. I mean, I don't know how, okay, so sure, so you get a timer interrupt every 1 millisecond.
Yeah.
And you update the VRAM time.
Mhm.
Then you say that there's a concept of a slice, a slightly longer period for which the task can run, which is longer than 1 millisecond, but let's say 10 milliseconds, I don't know, maybe 3, maybe you will explain how it works later.
Yeah.
And here you check whether you have to context switch or not, and if you don't context switch, you just keep running to the next, until the next tick, right?
Mhm.
But the ticks are static in there, so they're
Yeah.
not like,
Every 1 ms.
and then, okay, so this is one pass, so scheduler. And wake up is that, imagine you went to sleep,
Mhm.
and I assume when you went to sleep, you use the CPU to the next task.
Yeah.
And so we don't really know what happens here, but when you wake up, you include back into a red black tree.
You first insert it into the tree, and then you check if it preempts the current task or not.
Okay, you update current because you say, okay, it's almost like we might have to make a scheduling decision. That's why we update you.
Mhm.
What is NQ entity?
NQ entity is just placing the waking up task into the RB3.
Yeah, it's inside the NQ.
Yeah.
And then
once you place it in the RB3, then you check if it preempts the current task.
okay.
Yeah. So the rescheduling decisions are made only at 2 points, every 1 ms tick, or when a task wakes up.
No, but also when you yield as well, right? So you
Yeah. Yeah.
And what's your execution flow 3?
Execution flow 3 is exactly how the context switch happens. So once you have a reschedule called, that's when you kind of pick the next entity, which is the leftmost node in the tree. That's the simple part of CFS. But then that also introduces a lot of edge cases that they kind of had to optimize for, which is why it grew from 3,000 lines to 13,000 lines. But after that, you enqueue the previous entity, and then you pick the next entity, you take you out of the queue, and then you context switch. Yeah. And coming to the slices and exactly how, going back to this slide here. Yeah, going back to this slide here, when we're talking about preempting the current task, that's where we need to understand a few things. We come to a few concepts called the slice assigned to the task, which is based on the weight itself. And Linux has a few constants to kind of make sure that the performance or the trade-offs between the throughput and the responsiveness don't get hurt. And that is done through minimum granularity and then the scheduling period. So the minimum granularity in Linux, the default value for this is 0.75 ms. And this is the minimum amount of time that a task has to run when it is scheduled. So it cannot be preempted before this value because this is the minimum time that it needs. And this is basically there to make sure that the throughput is not affected by context switching overheads. So context switching, when we talk about what that is to kind of evict the previous, remove or clear the registers of the old task, load the new registers, as well as some potential issues with cache pollution and cache warm up, right? So the direct cost would be somewhere between 1 to 5 microseconds of context switching. And the indirect cost of cache warm up would be somewhere between 1 to 50 microseconds. So that's why they've chosen a value of 0.75 ms for the minimum granularity or the highest frequency of context switching, basically, meaning that 0.05 is the cost of context switching itself when we're talking about ms, and that would be somewhere around 15% of CPU. But if you go lower than this and you go like extremely granular with 0.5 ms minimum runtime per task when it's scheduled, then yes, you'll have much better latency because it's the scheduling decisions are done much quicker. But then that you're also talking about 50% of your CPU just going in overheads with context switching. So that is why you have this minimum granularity value that is set to 0.75 ms. And that is the minimum slice that a task can get. And the maximum slice that a task can get is set as 6 ms. And that is again to make sure that latency doesn't suffer. So if you have more than 6 ms, that means that a task has to run 6 ms, cannot be preempted, and any waking up task has to kind of wait 6 ms before it's scheduled again. So this is why you have these constants that are set by default. But the minimum slice the task can get is 0.75 ms, and the maximum it can get is 6 ms. And the scheduling period is basically the amount of time within which all of the tasks within the arbitrary have to run once. So basically, if you have the default scheduling period of 6 ms, if you have lesser than 8 tasks, this divided by number of running tasks. So basically 6 by 2 will give you 3 ms per task. This is the slice per task. So it's the scheduling period divided by number of running tasks.
What's you said 8 tasks and then.
If you have lesser than 8 tasks, you get more than 0.75 ms. If you have more than 8 tasks, the minimum is enforced and you have 0.75 ms per task, but then the scheduling period is adjusted. It's not the default of 6 ms, it's 0.75 into number of running tasks, and that's your scheduling period at that point. So if you have 16, you will get 12 ms scheduling period. And this is used in the slice calculation when we're talking about the minimum runtime that each task has to run. So we need to first understand that the minimum granularity value here is there to make sure that context switching overheads don't kill the throughput of the scheduler. And also we need to understand that these values end up giving us the scheduling period here. And the scheduling period is used to calculate the slice adjusted by weight that is used to kind of preempt a task. So now we'll understand exactly how the slice is calculated. So we know that minimum granularity is picked and determined by the number of running tasks and this value here. Now, once we have the scheduling period, let's say it's 12 ms, the slice is calculated.
Just an example, right? I don't know.
Yeah.
If there are 5 tasks, can you run us
Okay,
those numbers so we understand?
Let's run with 5 tasks. If you have 5 tasks, it's lesser than 8. So you have a default scheduling period of 6 ms. The per task slice that is given is 6 by 5, which is 1.2 ms, right? Now this is adjusted by weight later on. So this is just like, if you just take a CPU and divide it by the number of running tasks, you get this base slice. But this hasn't been adjusted with the priority yet. So if you have different priorities, let's say,
You get this 1.2 ms, and what is this number?
this is the slice, base slice that has not been adjusted to the weight yet.
Minimum granularity.
So
No,
essentially.
minimum granularity still stays at 0.75.
Why should every process get the same minimum granularity?
That's to make sure that regardless of the weight, the context switching overhead does not eat into your throughput.
Yeah, I understand that, but
Mhm.
but like my process might not even need that much, right? 0.75.
Yeah.
So if I'm done before 0.7, I still
Mhm.
wait.
Yes.
the
No, because then you're yielding, right? So then you're yielding and you get preempted regardless. So this is making sure that if your task needs more than 0.75 as well, it is not lesser than this.
Okay.
Is the minimum granularity. But if you have a task that yields before this, it is preempted regardless.
So wait, let me just maybe ask a couple of questions to clarify. So what it means is that no matter what distribution of priorities you will have, each task will run at least once in this 6 millisecond period.
Yes.
It's kind of like flipping those queues in a O1 scheduler.
Yeah.
Where you say, look, your higher priority, you ran for a little bit, but you still will, like your 6 millisecond, you will have to wait for everyone else.
Yeah, and the reason this is so confusing is actually exactly kind of like, outlining why CFS is not really founded in mathematical guarantees. It's all based on heuristics. It's all based on like reasoning and logic. So when we're talking about the scheduling period, that is important because that is how we reason whether the fair share of CPU was actually given over time. Because if we don't have that heuristic, we don't really know over time how to really see if a fair share of CPU is given or not. Right? So that's again a heuristic that is taken here. It's not really like, completely founded in mathematics, but you will see that if we go over the scheduling workflow or the execution flow, over different scheduling periods, the fair share of CPU is allocated to each task based on its weight. But what we understand here first is that minimum granularity exists because of context switching overheads, and it cannot be lesser than that. Yeah.
So suppose we have more than 8 tasks. So we get the minimum granularity. Then you said adjust for priority. Is it then possible to have less than 0.75 after adjusting?
Yeah, so that gives you the adjusted slice itself. So let's say I have 12 ms, which is the scheduling period for how many tasks is that? 16 tasks, right? Because 16 tasks each need 0.75 minimum granularity, the scheduling period ends up as 0.75 into 16, which is 12 ms. So the base slice itself is 0.75 ms that we determined before. But if we adjust it to the weight of the task itself, it determines the slice based on the priority. Now, if it's nice value 0, then it stays at 0.75. But if it's a nice value higher, then it gets a bigger slice.
What is, say 16 tasks, what is 12 ms? It's
The scheduling period over 12 ms.
But slice is still 0.75.
Yeah, so this is the base slice that hasn't been adjusted. So if we look at the code
But
itself,
typically we have 100 of tasks, hundreds of tasks. Let's say roughly 100 running on a server, maybe 200, something like that.
Yeah.
So if you multiply by 100, then the scheduling period will be 0.75 by 175 seconds or something like this.
Yeah. So here you can see that you have the number of running tasks. This is the shed slice itself. We calculate the wall time slice from the period by taking a part proportional to the weight. So you have the number of running tasks. Then you have shed period. Yeah. Oh, sorry about that. Let me just do that. Is it better? Oh, I think that's okay. Yeah. So basically, this is a shed slice that calculates the weight adjusted slice per task. Now you have the number of running tasks here, which is then passed into this one here. So slice is equal to shed period of number of running tasks. So what this guy does is determine the shed period itself. So the shed latency, the default value I told you guys is 6 ms. So that's only if it's lesser than this particular value, which is 8. So if it's more than 8 tasks here, basically, if it's more than 8 tasks, what it returns is number of running tasks into min granularity. So that's 12 ms there in our example. But the reason we have shed period is so that we can determine shed slice, which is we take a part of this period and we scale it by the weight. And that scaling happens later on here where
if you go to the comment right before the function.
Yeah.
Yeah, this S equals
Mhm.
times P.
So P is the scheduling period itself, and big P is the proportion basically they're talking about. W is the weight of the current task, and RW is the sum of weights. Yeah. So you have 16 tasks here, right?
And wait, this would also be, it would be 0.75 plus this 0.75 SP.
Not
Or
really.
this would be 1, like the fraction would be 1.
Yeah.
And small p is constant.
Yeah. So you're basically taking P is the scheduling period itself,
Yeah.
and you're taking W by RW. So basically you're adjusting that. Yeah, sorry. This is the minimum granularity that you have, P. And then you're taking a proportion of that and you're either making it bigger or smaller based on the weight itself.
So it can go smaller than, oh, but the smallest fraction will be.
Yeah. But then the reason we're coming to the scheduling period itself is not really to make scheduling decisions, but to reason about fairness. Yeah. So the scheduling decisions later on, you will see in the code itself that in preempt tick, there is a different part of the code that actually enforces minimum granularity. It's not kind of built into this math.
Okay.
This is just a heuristic to kind of reason about the fairness. So why we're talking about all of this is to kind of outline the complexity of CFS when it's trying to encode everything into just VRuntime. So you're talking about slices, you're talking about min granularity. Min granularity is rooted in practicality that you don't need, you don't want over context switching overheads. But at the same time, we're talking about just reasoning about fairness here. It's not really enforcing that in this math. It's actually being enforced in check, preempt, take, if you look at the code itself. So here, this is called every tick. After the current is updated and you're allocating the runtime there, it's checking if it needs to be preempted or not. Now, how it does that is by calculating the ideal runtime. So the ideal runtime is the shed slice that you calculate based on this guy here. You have the shed period, you have the minimum granularity, and you scale it based on the weight itself. So you have a larger slice for a bigger priority task. Now, this is the ideal runtime that it would run in one scheduling period, right? So if it has run that much, then it will be preempted. So how that happens is you check the current runtime, which is the last exec runtime and the current exec runtime. Basically, it's calculating in this particular scheduling round when the current task was started, how long did this guy run for? Now, has this guy run for more than the slice that we calculated based on its weight? If yes, it's preempted. If not, it's not. So this is the logic that preempts it if it has run more than the ideal runtime. If it hasn't, then it'll check, has it run for at least min granularity? If it hasn't, then it just returns. It doesn't do anything, it doesn't reschedule. And if it has run for more than min granularity, then it checks the difference between the leftmost node. So you can see the pick first entity that picks the leftmost node in the tree. And it checks if the difference in runtime between the current task and this guy is more than this slice. So it's not just that, okay, fine, the min v runtime, if the current runtime is greater than min v runtime, it is preempted. That's not true. That is required, but not sufficient itself. So it has to be greater than min v runtime by a threshold. And that threshold is the slice. And this is kind of showing you that, yeah, over time, over the scheduling period, it is given its fair share of CPU, but it's not mathematically grounded. It's just that it approximates fair share through all of these heuristics. It's kind of patched in together. It does make sense in the big picture, but it's not giving you mathematical guarantees at any point of time. Any doubts here? Because I'm pretty sure this is all stitched together.
You guys go.
I was just gonna say, so in approximately 12 milliseconds of time,
Yeah, let's go. Let's just share period.
all 16 tasks will run at least once.
Yeah.
And they will run for at least min v runtime, but ideally slice.
Yes.
And the sum of those slices would be close to 12 weeks.
That's just some of those. Yeah.
Cool.
So basically, over this amount of time, you have 5 tasks. Oh, sorry, we started with 16, right? These 16 tasks will run at least once, and the share of CPU that these guys will get will be proportional to their weights. And that's because of how V runtime kind of increases over time.
16 won't stay constant.
No.
So how do you?
So the number of running tasks increases when a task is added, and that dynamically changes the scheduling period and the scheduling slice. So if you look at the update cur logic, right?
So the scheduling period is falling, that was the number of tasks.
Yeah.
which might introduce delay because you will have to wait
Exactly.
whatever your GUI will wait for those other 1,000 tasks to be
Yeah,
created.
yeah. And this also outlines that with workloads that are too large, CFS suffers. So if you have server farms, CFS is not really that great at handling too many running tasks at the same time because it has all of these complex heuristics talking to one another and they're not really very efficient.
I have one more question.
Yeah.
Say like at some point in time, we have 26 processes A to Z. A has run once.
Mhm.
Will it run again before Z runs at least once?
Supposedly
It could.
That's the answer is no, but
So CFS won't necessarily try to run every process once before running any process a second.
No.
Okay, so I can get rescheduled sooner.
Yes, yeah.
That's
yeah.
what I would assume.
Not initially, I would assume that, yeah, in one period, every task is run, but then it's not a continuous metric that it actually focuses on
Right.
to run one task, like, every time before the same task is scheduled again. No, that's not done.
wait, maybe I misunderstood. So what's the answer to your question? I
It's
thought
no.
that, Soham asked if A ran, will it run again before Z runs? I thought the answer is no, but you say what?
So basically he's saying that we have 26 processes. One of those processes is A and it's just run.
Yeah.
And then you have another process Z. And he's asking if it's possible that A can run again
Yeah.
before Z is run.
Yeah.
Yeah.
Like
And,
A runs for the second time before Z runs. For the
yeah,
first.
and depends on the weight. So
Yeah.
if A has a greater weight, yes. If A has the same weight, no. Because we run time
No, but
increases
if
at the same time.
A exhausted its own, what is it called?
Slice.
Yeah, slice or whatever, ideal runtime.
Yeah.
Then it will not run first, or it will.
No, it won't. But then that is all like, based on conditions, right? So there is a way that it can run again. And I'll give you an
No,
example
it
then.
can possibly run if it gets, if it
Preempted,
yields
yeah.
waits on IO, then wakes up,
Mhm.
and then runs again before Z, right?
Yeah, or if it's preempted by a waking up task as well.
Oh, yeah, or it's, yeah, okay, sure.
Yeah.
Well, I was only asking about like naturally rescheduled, but I'm thinking that can only happen at a point of time T where Z has actually run for long enough to have a large.
If there is no waking up task and we're just talking about CPU bound tasks and it's not preempted for any other reason apart from the tick itself, then no.
I know.
No, because we're talking about only two places where reschedule is called, right? The tick and the waking up task.
Yeah, I'm thinking just takes.
If just this, right?
Yeah.
So this reschedules the task, it schedules A, right? And the only time it is preempted is when this guy consumes its slice.
Yes.
Or it's preempted because of this condition here. If the difference between this guy and this guy is more than its slice, which is basically saying that it's run for this duration
Yeah.
in this round, right? So if it has run this much time and it's preempted after that, then when this is scheduled, this cannot be scheduled again, basically, in one round.
But
I think I spoke a little too much. Yeah.
no,
but, yeah.
I followed what you said. I'm
Yeah.
just thinking that like A's V runtime after the slice is over can still be lesser than Z's.
No.
Not if they're the same priority,
Mhm.
different priorities.
Yeah.
But in the same period,
Mhm.
same scheduling period.
Yeah.
A can run,
Mhm.
complete its slice,
Yeah.
and still have a lower V runtime than C.
No, because like we're talking about when it's preempted, right? It's completed its slice. Okay, I think we'll have to look at an actual
I
number
wanna derail,
to
so we
really,
can come back to this, set.
But yeah, I think I understand what you're trying to say, saying that, okay, you know what, based on its weight, the VLAN time can increase, yes, and it can actually finish its V slice, but it can still be lesser than the VLAN time of this guy,
Yeah,
which means that this is going to be scheduled quicker, which is like, coming back to the whole idea that in an RB tree, you have higher priority tasks that stay on the left side longer.
yeah.
And then you have the lower priority tasks on the right side.
Yeah,
So basically, if there's a higher priority task, it stays closer to the left side and is rescheduled more
yeah,
frequently.
so like if
Yeah.
this is the lower priority one, this starts here and then it gets rescheduled here, but it's still like left of this guy.
Yeah, but we're talking about this in a way that we're taking this guy out completely, right? The waking up rescheduling. So if you're just looking at the tick itself, then that's not a possibility.
Okay, so with the ticket, we definitely go there.
Yeah.
Okay.
But if you combine all of the heuristics together, that's when it stays on the side, regardless.
Okay.
Yeah.
Thank you.
So coming to the execution workflows, right? Did we understand that one, this happens every 1 ms and the rescheduling decisions are based on whether it is consumed the vSlice or not?
Yeah.
Like any questions around that part? Just every tick, there is the update cur called where the v runtime of the current task increases. And if it increases beyond a certain threshold, it is preempted. That's fine. Then after that, we're talking about the task wake up, where one task is woken up and it's placed in the RB tree itself. Now, this is where it prevents spawn attacks. Child processes shouldn't really consume or overpower the CPU, as well as wake up attacks as well, sleeper attacks, where it takes up undue credit because it's not really increasing V runtime. For that, I think it's best that we go through the code itself.
That high priority processes with low, like extremely low CPU bound time suffer in these.
High priority processes with extremely low CPU bound time.
Yeah, like every cycle it needs very little amount of CPU time. This kind of suffer in this.
So you're talking about IO bound tasks that need short
yes,
bursts.
yes.
Yeah, it does. Yeah. So that's another drawback, because basically the drawbacks of CFS, if you look at real workloads, come up in two scenarios. One, when you have large workloads, too many running tasks at the same time. We already spoke about how it needs to recompute shed period, slice, everything is adjusted with that logic, as well as mixed workloads where you have latency sensitive UI workloads and compute heavy workloads at the same time. Yeah, because that's when all of the heuristics kind of have to work with one another. The buddy heuristics that I mentioned where there's relationship between tasks, as well as these heuristics where you have a task that is sleeping multiple times, but it needs less slice, like a smaller slice, but its priority is higher. So what CFS reasons about is that one particular task is given its fair share of CPU and full stop. It doesn't reason about latency and it doesn't reason about responsiveness separately. It just looks at making sure that this is addressed and it hopes that this takes care of everything else, which is latency as well as throughput. So to give you an example there, right? So if you have two threads, one is for a frame rendering thread, you know that this is extremely latency sensitive and it has short bursts, but it needs to be implemented at, let's say, every 15 ms. And you have another CPU bound task, but it's less priority, which is like logging, let's say, and that does not really have any latency requirements. It can be even 100 ms, it's fine, but it's got a lower priority, low weight, high weight, but it's latency sensitive, meaning that it has to be run every 15 ms. That's the requirement here. But what CFS will make sure is that it gets its fair share of CPU time, which is determined by the priority alone. So it will get, let's say, if you have just these two tasks and you have a 10 ms, 6 ms, right? So in that 6 ms, let's say this guy gets 4 ms and this guy gets 2 ms. This won't really show you exactly what's happening because the scheduling period is less. But let's say there's other tasks as well, and the scheduling period is 100 ms. So what CFS will make sure is that this guy gets its fair share of CPU, but it will not make sure that it is implemented or start executed every 15 ms.
Yeah, it looks like for these kind of situations, O1 scheduler was actually better.
No, but O1 suffers as well, because the moment you flip the moment you put
You'll have to wait.
the frame rendering on the other queue, active and active, it ran once,
Oh, yeah, the same.
then you moved, and then you have to
No,
wait.
but then it at least guarantees that,
No, but depending on how big the active queue
yeah,
will still waits for it. And here, the same notion baked into this scheduling period idea.
Yeah.
And I still don't a little, like, I'm still suffer to understand why this guy didn't show up in the front of the queue again. So why is that? It's just that because the logic of the scheduler is probably adjusted in such a manner that the renderings v runtime will never be less than whatever, than the rest of the 10 tasks, which are low priority tasks.
So basically what happens here is CFS makes sure that this guy gets its fair share, but it will not make sure that it's executed every 15 ms. So basically the urgency of the task cannot be specified at all. You can only make sure that it gets a fair share of CPU, that's about it. And it will work more or less like, 90% of the time because of its VRAN time growing slower. So it's scheduled more frequently. But at the same time, you cannot guarantee this. You cannot guarantee that it's always run every 15 ms. So that's where EVDF comes in to the picture there.
One small quick question.
Yeah.
Might have missed this. Does the amount of time, if you yield before, if you're giving X time slice,
Yeah.
you yield before that, how does that affect your VRAN time? Why does not affect?
It does affect it. It just increases it beyond the current scheduling period.
Because intuitively it feels that if you have a high priority rendering task, you can yield multiple times. So for example, it says I ran for 15 milliseconds. I yield it, or maybe I ran for 5. If I yield it, and then it means that by the time I'm woken up on a timer, imagine that it's a timer. It says I get to sleep on a timer for 15 milliseconds. That time when it's woken up can be placed again in the beginning of the queue and run again. If I understand correctly, right?
Yeah, so that's where place entity comes into the picture, because basically when you,
But still it somehow doesn't work.
Mhm.
Say that there is a reason when it might not work, but I don't.
Yeah, so that's why we need to understand what exactly happens when it's placed back in the queue. Because when we went over the wake up task flow, right? When a task is woken up, first it's placed in the queue itself, and then you check whether the current task is preempted or not. So this is again showing you the complexity of CFS, because you have to adjust the VRAN time of the task when it's enqueued. And based on that and the current runtime, you're checking if the preemption happens or not. So going to the place entity itself, this is where you prevent the spawn attack and the sleeper attack, like I mentioned before. So first it checks if it's a new task. And if it is a new task, the base is always the VRAN time. It cannot be lesser than that when it's added to the RB tree, because we spoke about how the VRAN time, min VRAN time never decreases. It is always increasing. So that's the base. So when you're adding to the RB tree, it cannot be lesser than that. Now, after that, are you going to kind of adjust it based on whether it's a new task? Yes. You're going to make sure that it's incremented by vSlice, which is what that process would run if it were to be scheduled in the current round, right? So you're adding that to this VRAN time so that this new task is not run in the current round at all. It's run in the next round. So basically a newly spawned task cannot prioritize or get CPU time over the current tasks that are already in the queue. So that's how you make sure that the newly spawned tasks are not, sorry?
No matter what.
Yeah. Yeah. It's just checking if it's a new task, initial and shared feed start debit. Yeah. This is agnostic of the wait itself. Because after that, based on the wait, it is scheduled more frequently. You're just making sure that the newly spawned tasks do not kind of overwhelm the CPU.
So it just won't spawn in the current scheduling period.
In the next scheduling period, it will resume like normal workflow. And then coming to the sleeping tasks, it is given a credit. So you take the min v runtime. So this is your base. Now the sleeping task is given a credit so that it's scheduled quicker. You want responsiveness as well. And that credit can be anywhere between 0.75 ms, which is min granularity, to 6 ms. Now that is done here. So threshold is what you add or subtract rather from the VRAN time. Now that can be min granularity, which is 0.75 ms, share latency, which is 6 ms. And if it's a gentle sleeper, as in it's sleeping very frequently, then you're adding only 3 ms. Yeah. So basically, you're making sure that based on heuristics, you're adjusting the credit that you're giving to a waking up task again kind of bathed in heuristics and kind of optimized over 17 years because of different workloads. So this is what they've had to kind of do because they ended up thinking, okay, V runtime is the only thing we will look at. And what you're doing here is giving it a credit before you're adding it to the RB tree. And because you're giving it a credit, it's going to be a little lesser than this guy, right? When you're adding it. What you're going to do here is don't look at this line because this is again a patch that was done to kind of prevent an overflow when you're comparing V runtimes. But this is the actual logic here. You make sure that the V runtime is the maximum between the previous V runtime before it woke up, the sleeping task, and the newly computed V runtime. So your V runtime of the task itself can never go backwards. It cannot.
Yeah. You gave it a credit and still you took it away here.
No, we didn't take it away though. So this is comparing the old V runtime before the task woke up, which is really low compared to the min V runtime. So let's say we had a bunch of tasks at let's say 50 ms, B slept. And at that point, its V runtime was 5 ms. And then when it woke up later at like 200 ms or something, I'm talking about the time the CPU. Let's say B stays at 5 ms, right? But the min V runtime at that point becomes like 25 ms. And that means that the delta between these two is really high. What it's checking is comparing this value to the credit applied to this value. So you take this as the base when you're enqueuing the task, but you give it a credit. The credit can be anywhere between 0.75 ms to 6 ms. So you subtract that value from this guy and you make sure that you give the maximum of these two values such that the V runtime of B itself never reduces.
So it's like the other value that's being compared against is original V runtime plus period minus discount.
No, the one value is the original V runtime before it woke up at the point that it slept, basically. And the other value is the min V runtime plus credit, minus credit.
What does this do? SE runtime and V runtime? What is it?
Yeah, SE runtime is the runtime that was part of the task itself when it slept. It did not increase after that, right? Once it slept, it does not increase.
But what did we adjust the threshold? What did we do?
Yeah, so that is basically first we take the base value as the min V runtime here. And then we subtract threshold from that min V runtime.
So it can be on the left of the.
Yeah. So that's why you make sure that min V runtime never reduces because you have to clamp it at different parts of the code. Because they do that.
This is where this brain buffer will. So they can be waiting for everyone else to run. So it can sleep once, maybe will be woken up, will be given a credit, will run, right? But then if it goes to that again, then get sufficient credit to finish.
Yeah, so here we're making sure that the runtime of a task itself always increases, it does not decrease. And in update curve, we looked at min V runtime being updated, and that told us that the min V runtime as well is always increasing. So we're making sure that both of these are ensured, but at the same time, what you're doing here in place entity is two things. One, you're making sure that spawn tasks don't overwhelm the CPU. They're only scheduled in the next scheduling period. And you're making sure that the waking up tasks are given a small credit. So this is ensuring responsiveness, but you are clamping it. You are not making it more than 6 ms. So this is the largest value that you can give it, the credit. So it's not more than this. So basically waking up tasks, if they suddenly decide to run forever, they cannot do that because of vSlice. If it runs for longer than vSlice, it is preempted and it is not given a credit for more than 6 ms anywhere.
So like this, that if condition at the end, the max V runtime thing.
Yeah.
This will only really happen in the first 6 milliseconds of the schedule.
No. Every time a task wakes up.
But isn't this possible, like this comparison, isn't this only viable if the discount is because of the discount?
No, so basically, let's say that B slept, and when it slept, it was 5 ms, the V
Yeah.
runtime itself.
Yeah.
And when it wakes up, at this point, let's say the min V runtime was 5 itself, right? So it was a current task when it slept.
Okay,
So it executed, it slept. At that point, it was 5.
yeah,
And then let's say when it woke up, it stays at 5 ms, the V runtime.
Yeah.
But the min V runtime kind of keeps growing
yeah,
of the other task. And that point, it was 50 ms. So this is not the initial part of the scheduler, right?
Yeah, so
Yeah.
like, I don't see the original one ever being there.
This one, right?
Yeah.
Yeah. Oh, that's what you're saying.
Yeah,
that- Could it
I
be
think
that-
the original one can only be picked in like the first instance.
So this is for the other tasks as well. So basically, this is for the waking up tasks. All of this kind of like, is tied together because we are actually reducing the V runtime by threshold. But that's only for waking up tasks. We don't do that for normal tasks that are being enqueued. So for example, if
Yeah, but this V runtime is also being applied to the waiting of task, like SE.
yeah,
It's the wait time.
so this max comparison is
Yeah,
only for sleeping tasks, right?
so SE is the waking, oh, SE is the sleeping task.
No. So SE just refers to a scheduling entity. So
Okay.
that's a task. But
Yeah.
this is applied to any task that is being enqueued in the RB tree, this condition. But this is only relevant for, this is basically making sure that the V runtime never decreases, yes.
Yeah.
But this part is only for the sleeping tasks, the threshold. But this is for all tasks that are being enqueued. So for a normal task that is not waking up, let's say it was at 8 ms, it was preempted by the tick and not a waking up thing. So it grows more than V runtime, right? So I explained how for it to be preempted, the difference between the runtime of the task itself and min V runtime has to be bigger than a threshold. So at that point, it can be, let's say 8 ms and the min V runtime can be 5 ms. So when you're taking the max of these two, this will be picked, which is the actual runtime of the task, SE runtime. And then this is the computed V runtime. So if you talk about this case, right?
Sort of get it.
Yeah, for this case, you don't really decrement the min V runtime by threshold. So V runtime only contains the min V runtime itself. So when you're making this comparison, you're comparing just the min V runtime essentially and the old runtime of the task. So if this task is not a waking up task, it's a task that was preempted by the tick. It can be more than the V runtime.
I see.
So
Because
this-
the main V runtime has not been calculated for this.
Yeah, because min V runtime is just for tasks that are inside the tree itself.
Alright.
So since this guy is preempted after it's increased over min V runtime by a threshold, it is bigger, and that's when this is, yeah. But then this kind of shows that it's all based on heuristics, and the kind code is not reasonable by looking at it kind of like plainly. It's a lot of things working hand to hand to kind of give us a fair share of CPU over a scheduling period. So even this fairness that we talk about is reasoned about. It's not guaranteed. And when it comes to latency sensitive workloads, it suffers. And when it comes to a lot of running tasks, it suffers because of the complexity itself. So coming back to this,
Yeah.
Yeah.
Have like 5 minutes.
are you serious? We haven't even started yet.
Uh,
Okay, but maybe what we can do is really kind of appreciate what CFS tried to do is that it took everything that we talk about when we talk about fairness and make it just about V runtime. So in doing that, they started with 3,500 lines of code. They thought, yeah, we've got it. But then they quickly realized that no, we don't. So there's buddy heuristics that we spoke about when it talks about relationships between tasks. That wasn't a thing before CFS. It was made up only because CFS was in existence. So we're talking about relationships such as client server, waker wakey, and tasks that wake each other up for whatever reason, right? Those are buddies. And also you have something called the last buddy and the skip buddy. The skip buddy is made sure, entered into the logic to make sure that the same process is not scheduled multiple times repeatedly, consecutively. That's to make sure that latency doesn't suffer. And last buddy was made sure, added into the logic such that cache affinity is kind of prioritized. So if there is a way to kind of run the same task again, and it kind of helps your performance, then go ahead and pick that. So there's a lot of this logic built into the code, which made it grow from 3,000 to 13,000. But yeah, that kind of shows us how they tried to simplify it a lot, but they couldn't. It led to it becoming very complex, and it built on the heuristics there. It's not reasonable by math. It's very complicated, and it's a lot of things working hand in hand. And it was tuned based on the workloads itself. So
So this one, 2 to 6, right?
17 years, yeah, from 2007 to 2024. So this was there for a long time. They really tried to make it work. They added all kinds of patches. They tuned it as much as they could. And I think we'll come to that when we talk about the drawbacks of CFS. I think we can end with this today at least, because basically what we're talking about here is that, yeah, it is simple. It tried to make sure that we can reason about fairness by just looking at vRuntime, but it did not have an explicit model of lag. So for example, if we're talking about two processes that have the same weight, A and B, but B sleeps for very short periods of time periodically, then this will always get the sleeping credit. And over time, it will get more runtime than A, regardless of it's having the same weight as well. So it's got edge cases that they still couldn't fix after 17 years. It has heuristic based wake up handling and accumulated a lot of patches. So even if we look at place entity, right, this was added as a patch because basically if it slept for more than 104 days, it will run into an overflow condition. And they had to kind of add this as a patch. And there's multiple patches like this over the code. And I think this is also one of them, where the credit was reduced to 0.75 if it's idle, because they kind of wanted to tune the workload to make sure that CPU is not affected by idle workloads. Non-idle workloads are prioritized. But yeah, things like that, they had to add things over 17 years. And this is something that EVDF explicitly improves on, the urgency of a task. I think I gave you that frame rendering example. So things like that, where you have mixed workloads of UI as well as compute, that's where EVDF really shines. And that's why as soon as EVDF came out, a lot of big companies immediately jumped. They didn't really wait around for the next version. I think Meta jumped immediately, Android as well, because the UI workloads was the Android side of things, and the server farms was the Meta side of things, the really in a large number of tasks. Then when you're talking about interactive versus batch, we're talking about how CPU-bound tasks can get choppy throughput and interactive tasks can be overfavored, again, because of the wake-up heuristics. It wasn't really reasoned about mathematically. And then when we're talking about scalability and consistency, again, it grew from 3,500 to 13,000 lines. A lot of complexity was added. And yeah, you can kind of look at it as just guaranteeing a fair share of CPU, but not much else. Yeah. When you come to EVDF, what it really does is build on CFS. So when we're talking about the code workflow and the execution flow, is not really a blank slate. You're not really starting from scratch. You just do a lot more.
Here we should stop, but how many slides do you have about EVDF?
About the same amount, 15 slides. So I'm halfway through it. I don't know. Somehow I thought that I would just tell you guys what's happening and you'd be like, yeah, of course, that makes sense. But yeah, that's not what happened.
That has never happened. That's operating system.
Yeah.
Yeah, next time. So yeah, they wanna finish after the break.
Yeah, I really don't mind, and I think I would like to talk to you as well, because I'd like to kind of exchange ideas of exactly how to explain things. Because I thought I would go over the data structures first and then the actual functions, and finally come to the execution flow, which I thought would kind of communicate the idea. But yeah, as of now though, when it comes to just CFS, do we have a lot of questions as to exactly how it guarantees fairness, what the drawbacks were, anything like that? How does it guarantee fairness? As in over a scheduling period or over like, cycles of CPU, are we sure that it will kind of like, give it a fair share of CPU per task based on the weight?
I think as long as the total number of tasks doesn't change much, like I can see how it works.
Yeah.
My thinking gets very complicated when.
And if you think about C groups, it just like explodes.
I'm not even-
Because, yeah. But apart from that, do we know that, yeah, over time, it does guarantee fair share of CPU or approximates it to a good enough degree, and that it's completely complex when it comes to like, how it reasons about fairness. It's not mathematically grounded because we're talking about slices, we're talking about scheduling periods, and all of this is based on number of running tasks, which is not constant itself, and it is constantly updated. So everything is heuristic based, not mathematically grounded, and it doesn't give you any guarantees. So if you have workloads that need certain latency for certain tasks, there's no guarantee there. You cannot even specify that to the scheduler. So EVDF takes all of that. It does guarantee a fair share of CPU, but it adds on to that functionality by maintaining something called a lag and a deadline per task. And that gives you the guarantees that simplifies the logic of waking up tasks, preemption, and everything is mathematically grounded. Because the funny part of all of this is that EVDF was first published in 1995. So that predated CFS, but it took them a long time to actually go over to implementing that, because they did try as much as they could for 17 years and it just didn't make sense after a point.
I'm pretty sure even in that 17 years, there were a bunch of patches saying, let's try EDF and it just got.
Yeah. In 2023, there was the first implementation of EVDF, and then just a year later, they were like, yeah, screw this.
Oh, then, let's go.
But
How many lines of code is the new schedule?
it's not too much more. Yeah, because
Yeah.
that's true.
Wait, not too much more than 3,000 or 30,000?
13,000.
Oh,
Yeah. Because you still have the buddy heuristics and all the complex stuff there, it's just not used as much.